right, so welcome back to the interview series for quantum machine learning. So this series is trying to interview some young researcher working on quantum computing with deep learning. So especially quantum circuit learning, but open to most of the area. So idea is not really technical. It's like we want to share really personal experience and really deep human like idea about how people get involved to quantum machine learning, especially. So this is the second half between the for our interview between Dr. like Samuel Yanqi Chen right now in the like the national lab in the like Brooklyn, Brookhaven. Sorry, my bad. So in the first half, we just introduce and interact mostly with him, like how he got involved and how he learned physics from his high school experience and how he evolved and even eventually have two doctor degree. One is MD, one is PhD. And if you're interested, you can follow the previous series. But in this series, we are more talking about his experience developing the only first, I have to say that. Uh, so between variational quantum circuit and deep reinforcement learning. And also, I think back to the pretty first age with a lot of effort from different researcher like the Japanese researcher Maria Shaw working on VQC. But I think when we come back to engineering, it still have a lot of difficulty. So we are interviews how Yanqi designed his quantum circuit and how this quantum circuit amazingly work for a lot of application. So welcome back, Yanqi.
Hi, everyone.
So yeah, please.
So my work my very first attempt to include the variational quantum circuit into the reinforcement learning based on two papers only. The first one is the quantum circuit learning by a Japanese group, and the first author is Mitarai. And the other one is a paper from the Canadian star of Xanadu, and it's from Maria Shu. And that paper also provides a quantum circuit, variational quantum circuit architecture for the classification problem. So we have two papers, and at that time, I was thinking about how to build a function approximator to approximate the value function or the Q function in the reinforcement learning. And it's not that straightforward to borrow the circuit directly from these two papers because it's not that at that time it's not even easy to implement the circuit on the paper directly into a simulation software.
Yeah, I think if we look at the paper from Dr. Maria Shaw from Xanadu, and that circuit is amazing, but it's pretty deep and complicated, right? If you look at the connection between the gates, so like it's not surprising that they should be computation inclusive. And also, the paper from Japanese research group, they provide much straightforward like implement, but that circuit is not really clear enough, you know. So how did you come up with the idea to design a new circuit, and how did you combine this kind of idea like back to them like 3 years ago?
Okay, so when we try to build a quantum reinforcement learning model, and we first need to consider the environment. So the reinforcement learning environment that we consider is classical. So at each time step, the environment will feedback uh, a, a vector, of the state of the environment. And the quantum circuits need to encode these classical values into a quantum state. Okay, so this is the first obstacle. So how can we design such encoder? If we take a look at the paper from the Mitarai, they built a evolving Hamiltonian to encode the input state, but that Hamiltonian is designed to some specific quantum devices. At that time, we don't have our own quantum devices, so it's very hard to code the Hamiltonian directly onto the simulation software. And then after we encode the state, we need to process the state to do some transformation and some operation, quantum operation. If we look at the paper by the Xanadu, the 13th century quantum classifier, that paper, we can see that they provide a very good and powerful and expressive quantum circuit, but they use a lot of control rotation gate. The control rotation gate is a kind of 2-qubit gate, but that gate is very expensive in terms of the hardware implementation. So if we want to implement the control rotation gate on a quantum computer, it suffers from device noise. If we want to implement the control rotation gate on our simulation software, then the simulation is really slow. So actually, we cannot directly use the circuit architecture from either of these paper. So I designed a specially encoding scheme that can encode our discrete state space into the binary 1010 state into the quantum circuit. And then in the learning part, I use only single qubit rotation and the simplest form of 2-qubit gate called the control NOT gate or the C-NOT gate. And it turns out that with this simplified circuit architecture, we can still reach the similar performance in all of the testing cases that these two papers demonstrate. And we use this simple quantum circuit to implement our quantum reinforcement learning agent, and it turns out to be very successful.
Right. So how did you find out you can cut out the rotation gates? So you say that you use single qubit rotation gate, right? So I think that is really fun finding, especially engineering. And right now, a lot of paper use similar approach. And although they created our paper, your paper especially, on this kind of design, but how did you find out this kind of design works eventually?
Actually, in quantum computing, all quantum computation procedures can be decomposed into single qubit gate and control NOT gate. So right. The control rotation gate can be decomposed into control NOT gate and several rotation gate. The idea is that, okay, so we don't want to use the control rotation directly. We use its basic component, and that gates are usually more simple, and they can they are more noise tolerant.
Yeah, especially surprisingly good from from the experiment perspective.
Right, right.
And even now, if you look at Xanadu and Google Quantum, they do have a strong entanglement gate. Strong entanglement encoder, and I think that there is really similar to uh, like our previous attempts, and I think both are good solutions, like especially.
Right. So the so-called strong entangling are basically entangling any two neighboring qubits.
Exactly. Yeah. So well, so you find out this, you come up with this idea by combining and take out the advantage from those two papers, and you design your VQC basic model. But we all know reinforcement learning can be really tricky because in my in my first few years of my PhD, I mainly work on deep reinforcement learning, especially as if you know. But how did you find out? How did you pick out the environment and like you pick out some environment from the gym and also some application for channel control. And how did you pick out the like development and design environment and made problem more empirically?
Okay. So the first obstacle is to implement the algorithm itself. If you take a look at GitHub, there are so many reinforcement implementations either in the TensorFlow or the PyTorch. But of course, none of them are designed for a quantum circuit even today. Not to mention in 2 years ago. Okay, so the first problem is how to we integrate the quantum circuit into our say the deep Q learning or other policy gradient algorithms.
Yeah,
So
you have
this
to
is the first obstacle, and yeah.
Yeah.
And so at that time, PennyLand provides limited PyTorch support.
I see.
Yeah, and I just remember that I had some experience using the PyTorch to build a deep Q learning on the carport environment. So I tried to combine the PyTorch reinforcement algorithms with the variational quantum circuit. But after I built the reinforcement learning algorithm, I need an environment to test whether it can learn at all, right? So I tried a lot of different environments, such as carpool and a taxi drive experiment, and
the tax environment.
and the cliff walking environment is from the Sato and Bato textbook.
Yeah.
And
So
finally,
after trying this environment, you have to make the port and then run the experiment and waiting for training. How long it take when you select this environment?
At that time, I tried these experiments on my laptop. So it took me at least 1 or 2 days to rule out an experiment environment.
So eventually it'll take like 1 or 2 months, right? Before you find good development.
Several weeks. Yeah.
Oh, it's okay. Still good, right?
Probably a month. Yeah.
Probably.
The last trial is the frozen lake environment, and it's very successful.
Right. So the previous trying mostly they just didn't work. They fell, right?
Right. The agent cannot learn the policy, so the agent cannot reach the goal anyway.
Why it happened? You think it's because of the capacity of this dense mapping, or what can be the problem?
I think this is very hard to answer because the reason may be that the expressive power is not enough, or probably I didn't have a good set of hyperparameters.
I see. Because we find out there's some following work, and some people are trying to use WQN, and also
Right.
more recently, I think it's like 1 or 2 months ago, the Leiden group they also trying to use policy, and I'm also surprised they really make the experiment like works for couple. Right? You have the same feeling, right?
Right. Yeah. In the
Yeah, but
beginning, I want to build an agent that can learn the coupled environment.
but I think it's pretty hard because at that time you have to build everything from scratch, and you don't even know this project will succeed or not, right?
Yeah, because at that time I need a successful experiment to show my advisor that my research direction is okay, and I need some results. I need some positive results. So I
Yeah,
cannot put all my efforts
yeah,
to ask why cannot be successful in the couple. No, I cannot do that. I need an environment that can be successful. So I tried a lot of environment, and finally I found frozen deck is good. So when the reward converges to the optimal result, I was so happy that day. Yeah, it's uh June 6th, 2019.
it's almost 2 years, almost two
Right.
years. I forgot when I went back to Taiwan. So we meet that before or after? Forgot.
We met after
One.
I succeed in this experiment, but there is another challenge that I need uh, more different environments to test our agent. So we need to show that our agent can succeed in some different environments. But at that time, I only have the frozen deck examples. And
Yeah,
just
a little bit.
suggest
Yeah.
the example about the on the channel selection in the wireless environment.
Yeah, I think it's a funny experience. Like we guys didn't meet. I think we meet like it's my sophomore years during my college, and then we meet again like 4 years after. No, it's 6 or 5 years after, right?
I think it's 6 years,
6
almost
years.
6 years.
Yeah. So it's a nice story. Like we have a lunch together in the NTU hospital because like you know like he is still a doctor, so he is really familiar with the medical college in
Actually,
Taiwan.
I love the library.
Yeah.
So I do my quantum machine learning research in the medical library.
Yeah, after he finished his MD degree. So it's a amazing story. So back to then, I was in my second years of my PhD somehow, and I second to third. It's like it's my summertime, and I worked for reinforcement learning for a while, and like I think we began to discuss some coding problem on adversarial robustness or somehow, but eventually turned out to become the reinforcement learning. Yeah,
Right.
yeah. And I think one challenge back to then is like you have to kind of to scaling the development to see this quantum Q learning have some advantage compared to the classic reinforcement learning. And consider that the space information become really crucial. Yeah. And that's why I think we together work on that project, and I just provide the development with like controllable channel, like a concatenated radio, and to show up they have an advantage for more realistic computer network application. Yeah.
Right. And after that, we also had some more experiments. including the realistic device noise from the IB and quantum computers.
Yeah,
and even with this noise, our model can still be trained successfully, and the performance does not degrade. So it's a very promising result.
Yeah, I think it's still a really impactful work because they demonstrate that reinforcement learning and quantum machine learning actually could work, and also your circuit design just kind of simplify the requirement about the rotation gate and lower down the cost to implement this kind of approach. But if I remember correctly, I think at the beginning we trying to submit to some quantum physics journal, but you got a job in New York and you have to graduate pretty soon, and we submit to IEEE and then got accepted. Yeah, right.
Yeah, and I'm very happy to see that our this work has been cited by many subsequent papers, and actually I learned a lot from these papers, and um, um, they did some of the projects that I originally want to do, but other groups successfully performed experiments that I want to do originally, but I'm still very happy to see that this work has been noticed by many other groups, and at least I can say that some folks learn something from my paper, then it's good.
Yeah, and also remember you got info by Xanadu saying they invite you to participate the software computation research track.
Yes, and we got the first prize.
Yeah, I have to thank Xanadu AI, some of the audience there you are listening. Yeah, and we try to advertise you a lot, like during the presentation.
Yeah, actually, the Pentium package and the QLEX package from the Osaka University actually helped my research a lot, and these packages help us to build complex or scalable quantum machine learning architectures, and powered my subsequent works on the quantum convolutional neural network, quantum long short-term memory, and many more.
Right. So I think we still have around 3 minutes. Do you want to share some of your recent work, and also do you have any advice for people, maybe both senior people if they starting from physics to move to machine learning, or machine learning person move to the physics, or some advice on this quantum circuit learning, especially quantum machine learning? First, you can introduce some of your recent work.
Recently, I'm interested in the decentralized or distributed quantum machine learning. So there are two aspects. So the first is that we want to keep the data private on all of its participants. So we want to build a federated machine learning model, and on each of the client, they can train their own model and share only the model. And we show that in this framework, we can keep the data private, but the performance is similar to the original non-federated setting. The other aspect is that at the moment we don't have a very powerful quantum computer, but we can build several small-scale quantum computer. So such kind of distributed training can enable us to leverage the an array of small quantum computers to do something in large scale.
Right.
And
we still have some attempts on reinforcement learning, right? Some ongoing attempts. Yeah.
Right. I still hope to extend the quantum reinforcement learning to many other very complex environments.
All right. So thank you for sharing, Yanqi. So, do you have some advice or personal experience to sharing with those people starting, interest in quantum machine learning, or from quantum to machine learning, or from machine learning to quantum circuit, like experience, or do you have any new direction you think eventually will have a huge impact?
So for the quantum machine learning, I think it is still in its very early stage, and there are still many unsolved problems. And if you want to find a research project, I think it's very easy to find one. And there are two major directions. The first is the theoretical aspect, that you're using mathematical proofs to study why such models or frameworks even work at all, and how is their capability and their limitations. And the other aspect is the applications. And I'm more interested in the applications because I love build things. And if you want to find some research projects, and you can take or you can look at the classical machine learning problems, and each classical machine learning problems, you can ask the following questions: if quantum computers can solve this, or if quantum computers can it solve it better? Then I think if you use these principles, then I think there are so many interesting projects that you can work on.
Yeah, thank you for the suggestion. And we all know recently there's a lot since this year, the new combination between deep learning and quantum machine learning. Even there's self-supervised quantum machine learning, I think from the Oxford group. Yeah.
Yeah, it's really exciting in this field, and we expect that many more interesting work will come up.
Yeah, do you think do you have some short comment on this, device? We all know previously we can only work on, IBM machine, although we got a lot of support from both, really pioneer device. But starting this year, I think there's a different solution, by quantum cloud like Amazon, or some ASIC like the use TPU for this quantum simulation. Do you have some short comment on that?
So at the moment, I think directly training end-to-end training a quantum neural network is extremely hard on a real quantum computer, but we also see that there are many good and high-performance quantum simulators out there, and I think it's a good direction because these hardware or the high-performance softwares can help us build more complex or sophisticated quantum machine learning models. But in the end, we want these models to be implemented on a real quantum computer. I hope probably in 3 to 5 years, we will have much accessible near-term quantum devices, and then we can try these cool and fancy models on that hardware, and to see how's going on?
Yeah, I think the 200 qubits, like the IBM machine, is on the way, and also, the Google's TPU's simulation shows a lot of extremely well, like, performance. Yeah.
Right. Yeah.
Yeah.
So although I'm working on the only on the software, but actually I greatly appreciate the folks working on quantum computing hardwares. Yeah, because it made all these cool things realized.
Yeah, it's hard and much more risky. Yeah, but it's high risk, high return. Yeah. And yeah, and we also we so this interview series is not supported by any commercial or advertisement, and we do have some academic activity recently. So we have just accept like tutorial in International Joint Conference of Artificial Intelligence (EJCI). I think this year in August. So Yanqi and I will invite some invite speaker, and we'll work together to have a tutorial for quantum machine learning, especially for speech and language processing. Right. Yeah, and also we're gonna have a demonstration in the International Conference of Acoustic and Speech and Signal Processing (ICAS) later this year in May. So I think I'm still really appreciated, like, this area, like trying to incorporate with the idea from quantum circuit learning. So if you're interested, like by the end of this talk series, or you want to involve in the interview as from your personal experience, like we both of us are really welcome. And try to contact me, and we will contact you and to arrange those problems you will be happy with. And yeah, and all the series will be non-commercial, and it will be shared on Spotify and also on YouTube. Yeah. All right. So thank you, Yanqi.
Thank you, Hawk.
All right. So let's keep going, and hope you have a nice listening period. All right. Take care and goodbye.